So
Okay, we're recording.
okay, so calculus, I think calculus really is the mathematical recognition that whenever we measure, our measurements aren't absolutely precise.
Okay.
Like, say we measure someone's height,
Okay.
and we say that, he's 6 feet.
Okay.
But it's not really, he's almost certainly not exactly 6 feet.
Right. That's why we say 6 feet and somewhat inches. Right?
Yeah. Or even if he's closer to 6 feet than 5 foot 11 inches or 6 foot 1 inch. He might be like 6.5 inches or 6.25 inches or 6.000000001 inches. Feet.
So first, let me ask one question. What is good for?
Is good for computing things. Like calculus. Because sometimes mathematics, or in physics or engineering, we want a number, and the old methods of doing algebra and geometry, both of which are kind of exact mathematical methods, aren't really, they don't give good enough answers.
Okay.
So calculus is kind of a way to have our cake and eat it too. We approximate, which is kind of bad because there's an error. Because we're introducing errors whenever we approximate.
Okay. But at least we can get an answer where regular mathematics would say, you can't do this because
So that's one good thing. So that's the advantage of approximation over regular maths. But, the mathematicians kind of don't like this error function. So what they do is they say, alright, well, maybe we're always stuck with some error.
But Patrick, let me interrupt you 1 second.
Yeah.
Is rounding a form of calculus?
Yeah.
Okay.
Yeah. What? Yeah, it is in the sense I'm thinking of. It is in the sense of we introduce some error.
Okay.
I mean, rounding I would say is part of the theory of real, is sort of calculus for real numbers.
Let me tell you just a little bit of a funny story, Patrick.
Sure.
I was chatting with someone on the programming channel who said that round, seal, and floor functions should be eliminated from the standard library. And he said they only work in C# has a data type called decimal, which is for exact, it has precise, it's unlike a floating point. It will have a precise,
right.
What do you call it? A precise fraction to it.
Right.
He said, well, in that case, you can do it and get an accurate amount.
Yeah.
But he said that for floating point numbers, that he doesn't like the results of those functions. Yeah.
I think that I actually think that rounding to some decimal places is a very calculus flavored thing. Because in precise mathematics we'll have pi. Pi is great. It's the ratio of circle's circumference to its diameter. But we can't really use it to compute with, can we?
No, because it's infinite, right?
Yeah. So what we do is we round pi off. And then we say we can. And then we say, well, we'll just use the rounded off version. So always practice where we're doing these approximations. And what calculus is it's kind of a way to be precisely imprecise.
Okay.
If you like. It's a way to say that we do have to do some approximation, yes, but we can make this information good as good as you could ever want.
Okay.
Like no matter how small the error you want is, if you're willing to spend enough time computing, the methods of count can give you that an error. So you can never get a zero error. But you can get like a error of less than.
By the way, the word calculus sounds really scary.
Yeah, it does.
So,
Roman for pebble, actually. Roman for pebble, actually. Yeah. Yeah.
Oh,
Latin for pebble. Yeah, but it does sound scary. But it does sound scary.
Well, in Spanish, calcular means to calculate. Well,
yeah.
And it would seem like a variant of that.
Yeah.
Maybe be counted with, I don't know.
Yeah, I think that doesn't make sense.
Okay. So, you're saying that if I know rounding, I've used calculus already?
Yeah.
Okay.
Yeah, like rounding is sort of the count. So that's all good. I mean, what I'm really talking about here is the idea of limits.
Linux?
Yeah.
The operating system?
With an M.
Limits. Oh.
Yeah. So, like, you feel safe because you know that if you really had to, you could be precise.
Mm-hmm.
You know that you feel safe rounding pi off to 5 decimal places, say.
Mm-hmm.
Because you know that if the situation really called for it, you could go back and round pi to say 10 decimal places if you needed more precision.
Okay.
Or 20 decimal places, or 100 decimal places.
Okay.
And in the limit, you get pi.
Okay.
When you kind of round it up to infinitely many decimal places or something.
Okay.
And the study of calculus is the study of trying to make this, trying to make this infinite process meaningful.
Okay.
So the basic idea is that we have to, so the two basic ideas is that one, approximation lets us do mathematical tricks that we could before,
Mm-hmm.
and two, that in a lot of cases we can approximate as finely as we like. And, if we kind of, and we can kind of approximate infinitely well. If we took an infinite amount of time.
Mm-hmm.
And if we approximate infinitely well, then that's the same as having the exact answer.
Well, I don't think you can approximate, you're saying that we could approximate all of pi?
I'm saying that we could generate, if we had infinite time, we could generate all the digits of pi.
Okay.
And that would be pi.
Okay.
But we don't have infinite time.
Mm-hmm.
The more time we're willing to spend, the closer and closer we can get to pi.
Okay.
And so we have this convenient fiction that if we were to spend infinite time, then we'd get pi exactly.
So let me ask another question.
Okay.
If rounding's calculus, then what calculus is actually like the ways to implement different kinds of rounding?
Well, not just rounding. I mean, so sometimes rounding isn't all we want to do. Like, I'll give you another example of calculus.
Okay.
Say we have a really complicated shape.
Okay.
And we want to figure out the area of the shape.
Okay.
The calculus way to do it is to kind of draw rectangles kind of inside the shape.
Okay.
And so we just sort of tile the shape with rectangles, and we can measure the area of a rectangle very, very easily.
Okay.
And you know, the smaller and smaller the rectangles get, the better the approximation of the area. I mean, you can try this on a paper if you. I don't know.
I can totally imagine.
Yeah. Alright,
that's good.
I would think that using triangle would be better than rectangles, but yeah.
Yeah. You're right. I mean, I think they use in terms of actual computing, they can use triangles.
Okay.
Or trapezoids, they might use as well.
Okay.
Which is a kind of, you know, triangle, rectangle hybrid.
Right.
But yeah, you're right, the triangles would work better.
Okay.
But they use rectangles because it makes the math slightly easier.
Okay.
And they kind of rely on this infinitely small trick.
Okay.
Okay, so what was I saying? So that's another method of calculus of
finding areas. Okay.
Finding areas. And that is called integration.
Integration, okay.
And it has this very, it's denoted by this very scary symbol of an elongated S.
Okay.
Let me try and find it for you. It's amazing how much of math is just coming up with scary symbols in scary ways.
I don't know why.
I guess.
I think if calculus was more like something like fluffy bubbles, I studied it already.
Hang on, let's see. So yeah, this is the, if you click, I don't know what this quite works on it, but I can try and send it as a Unicode thing.
I'm accessing the link.
Can I?
Oh yeah, I've seen this. Yeah. I actually knew this had to do with calculus. I thought
now you know what it means.
It more looks like an F without the line.
Yeah. It does kind of, doesn't it?
And let me guess that the top part, means like the maximum and the bottom part means the minimum or something like that.
Yeah.
Okay.
Hang on. The top part means like the rightmost part of the shape.
Rightmost part of the shape? Okay.
Yeah, and the bottom means the leftmost part of the shape.
Okay. And like this formula that you sent me in the PNG file, what does it mean?
I'll tell you what that means. dx means width of the rectangle.
Okay, we're talking about rectangle, okay.
And f of the height of the rectangle.
Okay. Why don't they just put xy?
The way integration often crops up is because the shape on the area of is the shape was made by graphing.
Oh, is that what we're explaining the other with we're explaining, what were you explaining? What were we talking about? We were talking about
connotation.
Yeah, well, the last time we were recording something, you explained something about finding like an X and a Y by giving remember the time you were talking about the people spinning on the thing and when they drop off at a certain point?
I think I do remember that. Where the X and the Y are in the grid.
Yeah.
And
you'd express the X and Y as a certain formula instead of X and Y.
Yeah.
Is that the same as this?
Yeah.
Okay.
Yeah. Mathematicians for some reason don't like to just write X and Y.
Okay.
Physicists would have no problem with it, but mathematicians like to, I don't know, they like to keep track of where the X and Y came from, I guess.
Okay, and this formula form way of X and Y is like, it allows for an infinite X and Y?
Yeah. Infinitely small X and Y.
Okay. And so let me just to clear it up, this X and Y means like any point in a line from one part to another of a line, right?
Hang on. Like X is how left or right we are, and Y is how up and down we are. So
that I know. But about the fx and the dx, what would they?
F of x is the height and dx is the width.
Okay, so and the x in both things mean the same thing?
Yeah.
Okay, so what does the d mean?
The d means kind of change in x.
Okay.
Here's how the integral would work. Imagine like drawing a whole bunch of liquids.
Okay.
Say we wanted to integrate from 0 to 1.
Okay.
And we have some function f.
Okay.
Then we say...
I don't know what you mean by integrate from 0 to 1.
Okay. Suppose we have a function f.
Okay.
And we graph out the function.
Okay.
And we kind of cut off everything. Yeah, and we look at the shape between the bit where the graph has an x-coordinate of 0,
okay,
and the bit where the graph has an x-coordinate of 1.
Okay.
So we take this little vertical slice
of a line. Okay.
Of the line, yeah.
Okay.
And then we and to turn that into something that we can take the area of, we just draw like straight lines, going down.
I'm visualizing a little bit.
Imagine like a curvy thingy. Yeah, imagine like the ground as the x-axis.
Okay.
Imagine like a cloud thing. And imagine like two ladders dropping down from either side of the cloud.
Okay.
And that forms like a sort of squarish thing.
Rectangle, yeah.
Yeah. Forms like a sort of rectangle, but it's not really a rectangle because of the cloud.
Okay. So how does this relate to the x and the d?
So the dx, let's say for example that our dx was 0.1.
Okay.
So then we cut the shape generated up into 10 little vertical slices.
Wait, you're losing me. 0.1 times x. Do we know what x is?
Times f of x.
Okay, but okay.
I know how to do it. Imagine we have like a for loop.
Okay.
So we say like for x equals 0, x is less than 1.
Okay.
X equals x plus dx.
X equals x plus dx. Okay. How much, wait, dx a different variable from x?
Yeah.
So the fact that they both have was confusing me. I thought the x's were related.
Right. They are related, but dx so they're not like it's different variables.
Okay.
Yeah.
Sorry,
that is confusing.
So in this for loop, dx is a different variable. Okay.
Yeah.
This number would increment each time by the amount of dx, right? Yeah.
And every time
so are you saying dx would be 0.1?
Yeah.
Okay. And x is equal to 0 to x is less than, did you say less than 1?
Yeah.
Okay. So we're going from 0 to 1 thing 0.1 times each time.
Yeah.
So each iteration, the first iteration x would be, the first iteration it would be 0, the next iteration it would be 0.1, the next iteration would be 0.2, and so on until it gets to be 1.
Yeah, exactly.
Okay. Now I'm waiting.
So if we imagine that each time, if you imagine like we have a total running.
Okay.
So imagine that this for loop is used to compute the total area.
Okay.
Of the shape that we drew with the cloud and the lattice. So the first time we go through the for loop, we cut out like this skinny rectangle.
Okay.
And that rectangle touches the cloud at a certain point. And then we can get the area of that rectangle very easily just by doing width times height. And then we add the area of another different skinny rectangle which touches the cloud at a different point. And so on.
So we're trying to get the area of like the rectangle formed between the cloud, the edges of the cloud and the ground.
Yeah.
Okay.
Yeah.
So we repeat this until we reach the end of the cloud.
Yeah.
Okay.
Yeah.
And
why do we need one skinny rectangle instead of one very fat one?
If we imagine the cloud,
imagine the cloud with kind of,
imagine the cloud was an arch.
Imagine the cloud was an arch, say.
So it starts low, then it goes up a lot.
Then it goes up a lot.
Then it goes back down.
Then it goes back down.
If we had a fat rectangle, then we would kind of miss the arch bit. But if we had a lot of skinny rectangles, then we wouldn't miss the arch as much.
I think I totally understand that.
Alright.
So is calculus mostly used to get the area of stuff?
That's one of the main applications of it.
Okay. And you said rounding is a form of calculus too?
Yeah.
Okay. And so is seal and floor?
Yeah.
Okay.
Actually, I might have told a lie there. I don't think rounding is a form of calculus. I think the fact that we have to round kind of motivates rounding is a kind of calculus-like process.
Okay.
Yeah.
Well, in the fact that it's something imprecise.
It's an approximation. And it's an approximation that we can successfully refine.
Some other time I don't think this is related with this, but have you ever heard of bankers rounding?
Where they round in a way that respects the counting rules.
Actually, some other time let's talk about that and interested in how it works.
Yeah. So we can use calculus. Anyway. So and you can see with this for loop that if we make dx smaller, then we'd have a better approximation to the area.
Okay.
And if dx is infinitely small, well, the computation would take forever to run.
Okay.
But at the end, we would have the exact area.
Okay. Okay, so the smaller the slices of a the smaller the slices of a what do you call it, of a rectangle, the more higher definition we can get of the actual area between the
yeah.
Okay.
So this is great, because, there are a lot of times we want to compute area.
Not right now, Patrick, but I do want another time for you to re-explain this, how we calculate the... Oh yeah, we did it with the for loop, okay.
Yeah.
Why, again, I'm not really clear, why do you say mathematicians prefer using this f and x and dx to then just using an x and a y?
They prefer it because they're interested in studying functions instead of general shapes.
Okay.
Yeah.
And a function is something like a programming function?
Well, yes and no. It is, but it doesn't do anything. It just takes an input and returns a result, and returns an output. It doesn't like print to the screen.
So would this function be like enclosing the for loop in a function?
Yeah.
The for loop that we were talking about?
Yeah, enclosing the function in a for loop.
Okay. So this f could be thought of just like a for loop.
No. The integral sign.
Oh, that elongated S thing.
Yeah, that's the for loop.
Okay.
And the f is the function, like the f would be a function that's called inside the for loop.
What would it be in programming? F.
I don't know. For example, it might be.
You mean a function called Q?
Yeah.
Okay.
Or square root.
Square root.
Math.sine, say.
Okay. And, so if it, say it would be math.sine, cause I know that one. If we could replace the f with math.sine x.
Yeah.
And then we multiply that times d. Let's see, okay, so f is the for loop. So
S is the for loop.
S is the for loop, and you're saying that describe the for loop. You said we'd have x equals 0, right?
Yeah.
And then, how would this function go into that for loop? I'm unsure.
So what it would be is, it would be the for x is less than 1,
Okay.
x equals plus 0.1, total plus equals math.sine x times 0.1.
Okay. And 0.1 is dx, right? Yeah. Okay.
Yeah.
Okay. I think I get it. Should add this, I'll do it. Now that I have the recording, I'll add to the maths from scratch thing.
Alright.
Yeah.
So that's calculus.
In a nutshell.
That's calculus of areas.
Okay.
And that's a very important. So anyway, the reason this dx stuff is so important is that in some cases mathematicians can actually figure out
what would happen if
dx
was infinitely small.
Okay.
And they call that the limit of taking dx to zero. The limit of dx
goes to zero.
Patrick, can I interrupt you a second?
Yeah.
Okay, so I'm still, okay, I got the for loop thing, but I know this will make me sound pretty dumb, but, okay, now going back to thinking of shapes.
Yeah.
We replace the x with 1, we said, right? So in this formula, well, let's forget, is it possible to write without the integration symbols? Is it possible to write f to the x and then times dx? Is that possible?
That is possible.
That'll just give us a rectangle. That'll give us one.
Okay, that's what I want to know. Not a rectangle. It would give us a line from like the bottom to the top, right?
If we just write x.
Okay.
That would give us the line from the bottom to the top, and f of x would be the length
of the line.
Okay, how does that work?
How does that work?
Yeah, how do you get a line from the function?
I don't know, that's just sort of just the it kind of just follows from how we graph functions.
Okay.
Imagine functions were graphed in the following way. Imagine there was like I don't know. Imagine there was a kind of laser.
Okay.
That started at negative infinity.
Okay.
And just swept through the plane.
Okay.
And that laser at any given point. And that laser kind of like activated a whole bunch of chemical, reacted with a chemical trap. Or something like that. I'm sorry. Imagine that the laser is like burning. The laser is shining upwards.
Okay.
And laser stops. That's the value. That's the value of the function at that x coordinate.
Okay, so we gotta have a laser on the ground and we're shining it up to the moon. Does that make any sense?
Yeah. Yeah, that makes sense. Yeah, that makes sense.
So what's x and what's f in this?
So x would be our geological coordinates. Our latitude and longitude.
That seems it's more than one value.
Alright, let's just call it our latitude. Let's just call it our latitude. And F would be like where the laser gets blocked.
The position in the moon.
Yeah.
Some latitude of the moon.
Yeah.
Okay. I'm unsure how I thought F was a function, not a...
F is a function. F is the laser. F is the laser.
F is the laser, okay.
Yeah. F of x is where x is the latitude on the moon that corresponds to the latitude on the Earth from which we fired the laser.
Okay.
So, we fire the laser, it hits the moon at a particular point.
Okay, so x is the latitude on Earth, f of x is the latitude on the moon.
Yeah.
Okay.
Yeah.
Can we go to a little more let's go to a smaller scale. Let's say I have a square piece of, let's say I have a regular office piece of paper, okay? And I have my pencil in my hand, okay? Let's say I take the center of the center of the paper, the bottom part of the center of the paper.
Yeah.
And I decide to write a line that goes to the top right of the paper.
Top right of,
Okay. So, the bottom center of the paper is X.
Yeah.
Yeah? And somehow this function determined f of x would somehow be, we have to return the top right of the paper.
Yeah, I see the trouble. Yeah, the only way it would work is if you kind of like rotated the paper so that it was facing diagonally. Like, yeah, f of x would be a straight line going from the bottom to the point.
The bottom to the point.
Yeah, I'm not making sense, sorry. I mean, if we strip away all the analogies.
Okay.
The graph of the function is the set of all points whose x-coordinate is just x, and whose y-coordinate is f of x.
I think where I'm getting lost is how do we graph a function, and how does a function graph, how is it graphed?
I see. Alright, here's how it's graphed.
Okay.
Imagine that we have a function.
Okay. Now we're talking about a program.
Yeah, like math.science.
Okay.
And assume for the sake of argument that we're dealing with a monitor with finite resolution. So I'm using calculus again. So we start. So let's call the leftmost pixel. So we have to attach some kind of coordinate system to the pixels in our monitor.
Okay.
And I don't know how many pixels are there. Let's just say the monitor has 1,000 by 1,000 pixels.
Okay.
And the leftmost, so the leftmost column of pixels is the 0th column.
Okay.
And the rightmost column of pixels is the 999th column.
Okay.
Right. So how we graph math.sine is we go for x equals 0, x is less than 1,000, x plus.
Then let me try to guess. Then we do like sine x. And we'd put an arbitrary y in, right?
No. We activate the pixel at x and math.sine of x.
Oh, okay.
Yeah.
X and math.sine of x. Okay.
Yeah.
And then we do that for all the pixel. We repeat process. Okay. For all the pixels. Okay.
So we draw it one slice at a time.
Okay. Okay, now that's starting to make sense to me.
Okay, cool.
Now when we see this mathematical formula of f of x dx, when we have a space, when we have x times dx?
Yes.
Okay. Now the d and the dx and the, I'm sorry, the x inside the formula. I mean, the x inside the f and the x to the right of the d are the same x?
You should view dx as just a single variable.
Okay.
Just use dx as a variable with two characters. There is a slight, there's a kind of a reason it's called dx, but think of it as just a different variable with two characters for now.
If we did this for y, would it be called dy?
Yeah. So that's the kind of connection.
Okay. I know that in like game programming we use dx and dy to like express the speed that that like some sprite is moving.
Right. That's
the kind of thing.
Okay.
Yeah, that's the kind of relation.
Yeah, that's the kind of relation.
Okay.
Actually, speed is another version.
Another calculus for it.
Okay.
So think about how we would actually measure speed.
Okay.
Like how fast
something is going kill time.
Okay.
So the way we'd do it is we'd measure. So say I had a car.
Mm-hmm.
And the cops wanted to know whether I'm speeding or not.
Okay.
So, and let's say they can't check my speedometer because that would violate the Constitution or something.
Okay.
So what they do is they would set up two laser traps.
Mm-hmm.
Say 100 meters from each
Okay.
other. And they would measure the time it took between when my car hit the first laser trap and when my car hit the second. And the smaller that time,
the faster you're going.
The faster I'm going. Another way we could do it is say they didn't have any laser traps.
Mm-hmm.
But they have a GPS tracker.
Okay.
And if they measure the speed of my car, what they could do is they could look at where my car was
mm-hmm.
at a particular time.
Mm-hmm.
And then look at where my car was
at another particular time.
Yeah, like a second later.
Okay.
And the bigger the distance, the faster it's going.
And what about the way cops actually, if my dad told me correctly, I think it's true. Cops used to or still do measure like, they have some kind of gun that they shoot from their cop car to your car and measure the speed of your car.
I think it's a laser trap. I think it works by the laser trap principle.
Mm-hmm.
It's just that there's two lasers and they're very close.
But are those lasers on the road or lasers that the...
I see.
As far as I understand, it's a kind of gun that they shoot at your car to measure your speed.
Yeah. I think I know what it does.
And the cop car is probably moving too.
Yeah.
Yeah.
I think it would have been. You fire the gun. So like, what I imagine might happen is like one laser pulse hits the car, and we can kind of measure how long it took the pulse to reflect back.
Okay.
How far away the car.
And then we know the cop's car actual speed.
Yeah.
So we'd have to know how much faster if we were the cop, we'd have to know how much faster the other car is going than us. Yeah. Or slower.
I actually
don't know quite how the car works. It might be interesting to find out, but
I'll do it later.
Okay. It probably wasn't that what you were trying to explain. I'm sorry.
What I was trying to
explain is
let's look at this GPS
method more closely.
So like, say
in the mean,
say I was speeding.
Mm-hmm.
with the GPS mode. Say I had a GPS tracker and I was feeding. But before the GPS could ping me again, I suddenly slammed the brakes.
Okay.
So the result is that I didn't actually end up traveling very far afterwards. So then the GPS wouldn't detect me. Or rather, it would detect me.
But it would say you're going slow.
Yeah. Oh yeah, say I was going slow. But between pulses, between the GPS times, I don't know, I got hit by a truck or something, and then suddenly my car went really fast in the intervening time. Say, I don't know, I got launched by a catapult or something. Or I hit a landmine or something.
I think the opposite example was better. You were going speed limit and then hit the brakes.
That's a better example. So if the time between the GPS pulses was too slow, then I couldn't detect that. But as the time gets shorter and shorter,
it's more precise.
It's more precise, yeah. And if it was kind of infinitely short, then we would know the exact speed at which I was going at any given point. This kind of reminds us of the area thing. As it gets smaller and smaller, we get better.
So as long as if you were implementing the GPS system, you'd want to take the smallest GPS time as you'd want to get the GPS as quickly as possible.
Right.
So that there's no so nobody can slam on the brakes. And make them, and you'd get a wrong.
Yeah. So I think that's kind of a better description of calculus. Actually, calculus is what we have some process. And this process depends on a finite quantity. But we want to make this quantity as small as possible.
Okay.
And if it was infinitely small, then we'd get a perfect answer.
And with the scary S thing, how would that look for looking for the speed of the person that you don't want them to brakes?
The integration?
Yeah.
No, that's a different problem.
Okay.
Yeah.
You don't use integration for that.
No. I mean, the two are related, but they're different problems.
So not every calculus problem uses integration.
No. Not every calculus problem uses one of the two. So this problem is called differentiation because it's about finding differences.
Okay.
So it's sort of like in arithmetic. Integration is kind of like the equivalent of adding.
Okay.
Because we're adding infinitely small quantities.
Okay.
And differentiate is sort of the equivalent of subtracting.
Okay.
Or actually better yet, it's kind of like taking the average or subtracting.
Okay.
Yeah. So you might suspect that there's a relation between adding and subtracting.
Okay.
And there might also be a relation between integration and differentiation. And there is.
Okay.
But I'll tell you what that relation is later.
Okay. Okay, Patrick. Are you feeling sleepy?
I'm kind of sleepy, yeah. What's this? Oh, good.
Let me stop recording.